Welcome back to week 5, and in video 3 we will discuss the major types of winds and how they are caused. So we classify the different types of winds based on their scale and timing. There's 4 major scales: microscale, mesoscale, synoptic, and global. Microscale flow patterns happen last less than an hour and are about 2 kilometers or less in size, and they're caused by small scale pressure differences, and all of these types of winds are influenced by friction and other obstacles. Mesoscale winds are a little bit larger. They're 2 to 100 kilometers in size, and they can last from minutes to hours. Synoptic winds are even bigger, so they're about 1,000 to 5,000 kilometers, and they can last for days. And then global patterns are 2,500 to 25,000 kilometers in size and last for weeks or longer. So to give you kind of idea of what each of these are, microscale winds include laminar flow, turbulent flow, and cyclonic flow. Laminar flow, you can see here the wind is traveling basically pretty evenly across in the atmosphere. There's kind of a straight line, and because of friction on the surface, you can see that those speeds decrease as you get to the surface. The free atmosphere would be where it's uninhibited or unhindered by surface topography and friction. Turbulent flow, there's some kind of obstacle in the way that causes these laminar flow to be disturbed, and you can see kind of swirly patterns develop. And then cyclonic flow would be air that is spinning in a circle, kind of like a spiral staircase. Mesoscale winds include land-sea breezes. These develop due to temperature differences during the day versus the night. So during the day, the land heats up, the air above heats up, that air rises because it's less dense, and it ends up cooling and sinking over the ocean, producing this convection cycle, which then reverses at night. The oceans, because the oceans have higher heat capacity, stay warmer longer. So we have a low pressure that develops over the ocean, air rises, and then sinks over the cooler land surface, and we get this opposite flow pattern. So at night we have land breezes moving out to the ocean, and during the day we have sea breezes coming in towards the land. We can also have mesoscale winds around mountains and valleys. So this happens along Mount Hood quite often. So during the day, the land heats up and it rises up around that mountain. We get clouds that can form above, and then at night sinks on either sides of the mountain because we have the air and the ground cooling at night. We also have synoptic scale, so these are cyclones and anticyclones that develop around high and low pressure centers. Your book has a great diagram and description of what these are. Basically, cyclonic flow is where we have air flowing up and into low pressure zones, so we see it coming into that low pressure zone and then it moves up into the upper atmosphere. Whereas around high pressure zones, we have anticyclones where air flows down into the center of this high pressure zone and then out around on the surface. So here you can see an example of what a cyclone would be. Those cyclones and anticyclones can produce what are called ridges and troughs in the upper atmospheric circulation patterns. These happen when we have high pressure zones. We have the upper air currents forced up and form these ridges. Looks like a mountain on a map, and then at low pressure zones, they're diverted southwards, and we see troughs that form. And we also can produce what's called convergence and divergence in those upper air currents. So we have, as we come into a trough, the air is being squished, converging into a smaller area, and then as it comes out, it's spreading out and diverging. So here are just a few of these cyclones that you can see in the tropics. We can also have synoptic scale winds, so things like Chinook winds, that warm, dry, downslope winds that result from cold air to the east of the Rockies that combines with mild marine air coming from the Pacific, and then we end up having that air warming adiabatically as it descends from the Rocky Mountains and produces these kind of weather patterns that you see here, and this usually occurs in the wintertime. We also have Santa Ana winds, hot, dry winds that come from the land, travel over mountain range and sink, and then travel out to the ocean. So this is in California, pretty common, because we have a high pressure zone where air is sinking over a desert, and then it travels over the surface, warms adiabatically as it descends into the basin. We see this in autumn. It produces hot, dry conditions where we see a lot of wildfires. So these are bad for wildfire season. We also see nor'easters on the east coast. These are low pressure centers that travel across the U.S. We end up with this cyclonic flow. You can kind of see the clouds forming this curved pattern here. And these are very, very intense. One side might have blizzard-like conditions, and another side might have freezing rain, thunderstorms, tornadoes. And if I have a link here to the NOAA Nor Easters website, it's also linked in the videos for this week. Definitely check that website out. We also have lake effect snowstorms that can hit the east coast. We have warm lakes. Here you can see Lake Ontario and then some of the other Great Lakes here under the clouds. As this cool air travels across these warm lakes, we end up having this cold, stable air moving over this warm body of water, and we end up having a lot of evaporation occurring, and then we end up with tons and tons of snow that falls. Here you can see just how much snow, like 2 to 3 feet or more, that can fall in one storm. We'll talk in more detail about all these different types of storm systems in a few weeks. We also have global circulation patterns. Again, I have a link that you can visit to check this stuff out in more detail. These are involving the entire globe. So there's 3 different circulation patterns that have developed. The first one is tropical flow. Here where we have at the equator, we have the most solar radiation reaching the Earth's surface, highest sun angle, lots of heat and energy to heat up the water and the air and the land, so that air rises, cools, condenses, produces clouds around the equator. It can also end up sinking and then heating up again as it travels across the surface. So that's the tropical flow. You also have the polar flow, which is up here in the polar regions, where cold air sinks, travels across the surface, and then rises as it warms up. And then in the middle here, we have the subtropical flow in our neck of the woods. And this is kind of the gear in between the tropical and the polar circulation patterns. So these 3 patterns actually help to produce the polar jet and the subtropical jet. So what we see here, if we go from the equator, where we have air rising, cooling, condensing, raining, and then sinking, at 30 degrees north, we have the Ferrel cell here, which is the subtropical cell. And wherever we have that air rising, cooling, and condensing, we have clouds forming. And then over here, we have the polar cell. So in between each of these cells, we have these jets that develop. And if we look here as our cross-section, each of these jets, the subtropical jet is forming right here in between 1 and 2. Polar jet is between 2 and 3. And here you can see where approximately each of those jets occur. And this is going to be motion of the upper atmosphere around the globe. So that kind of wraps up the different types of winds and how they are produced. Please check out the websites and your book for details.